Miss Sparky is graduating from ASU, and it's the best day ever, for she has two similar job offers in front of her, but vastly different salary options. She needs to decide which job will pay the best. For both jobs, she will work 40 hours per week. Now, for job offer A, she is offered $5,242.88 per month. And for job offer B, she is paid 1 penny on day one, and her salary doubles every workday. The first offer sounds like a lot of money, but she's intrigued by the second offer, because who would really offer a penny for a day's work? What is she missing? So Miss Sparky decides to figure out what her salary would look like in the month of June. So she takes out her calendar and places a penny on the first day she would work, places 2 pennies on the second, and then hits herself in the head, realizing she could simply fill in the amount by hand she would earn each day. So she fills in the second week and isn't very optimistic because on that Friday she earns only 64 cents for a hard day's work. But since ASU grads are always optimistic, she keeps filling out the calendar, still wondering what she is missing. But for Friday of the third week, she will earn $20.48 for a hard day's work. But then for Friday of the fourth week, she earns $655.36. Now that's more like it. Continuing on, she gets to day 20, where her eyes just pop out of her head. She earns $5,242.88, the exact amount the other job offer would have paid for the entire month she earned for just that one day. On the last day of the month, she earned an incredible $20,971.52. She marked in the calendar not to call in sick that day. Mathematically, let us compare the two job offers. Each job offer can be modeled by a function where each function has an input, which is the number of days she worked, and an output, which is the number of dollars earned that day. Now for job offer A, we have a constant function. Since she is offered $5,242.88 per month, this comes to about $238.31 per day. For job offer B, we have a function that models successive doubling. We start with a penny, which is .01 in dollars, and for each passing day, we multiply by 2 to attain the next day's wage. What we see is an exponential function that models successive doubling, and this function is g of x is equal to 0.01 times 2 raised to the x minus 1. Notice how quickly the outputs of the exponential function grow. It took 16 days for the amount she earned, or the output of the exponential function, to surpass the output of the constant function, and after that, the amount she earned skyrocketed. In fact, the limit as x approaches infinity of any exponential function, with a base greater than 1, will always exceed the limit of any polynomial function. Listen to the 2 instructional videos to learn more about exponential functions and their limits.